All right, welcome back everybody. This is our second video in our series for section 5.9 of AP Calculus, connecting a function, its first derivative and second derivative. We're going to pick up where we left off. We just finished example 3, so we're going to go ahead and turn the page and look at our last couple of examples. All right. So let's see, back in Unit 4 we talked about what information which told us that something was speeding up or slowing down. A little callback to Unit 4. An object is speeding up if blank and blank have the same sign, but slowing down if they have different signs. Do you remember what those two things are that fill in the blank? I hope so. It's speeding up if the velocity and the acceleration have the same sign, but it's slowing down if they have different signs. And we're going to utilize that relationship in example 4 here. Example 4. A particle is moving along the x-axis with position function x of t equals 1/3 t cubed minus 4t squared plus 12t. First we're going to find the velocity and acceleration functions, and then we are going to describe the motion of the particle. So we find the velocity function. That's just going to be our derivative of our position. So that's going to be t squared minus 8t plus 12. And then our acceleration function is the derivative of our velocity. So that's going to be 2t minus 8. Now to help me describe the motion of the particle, I'm going to go ahead and make a sign chart for each of these. And in fact, I'm going to line my sign charts up so that we get the overlap with one another. V of t is equal to 0 here. Let's see, that's t minus 2 times t minus 6. So t equals 2 and t equals 6 are our critical points, and the acceleration is equal to 0 at t equals 4. So all right, so I've got my sign charts lined up so that I can analyze what's going on underneath. Now I'm just going to go ahead and fill in my sign charts. If I put 0 in for velocity, it's positive. If I put 4 in for velocity, that's going to be 16, that's going to be negative. If I put 8 in for velocity, it's going to be positive. If I put 0 in for acceleration, negative. And if I put 6 in, it's positive. Okay, so there's my sign charts. And we can see the overlap here, like for instance, from the beginning of time, wherever time begins, maybe we should have said time started at 0, but doesn't matter. From the beginning of time here, the velocity is positive and the acceleration is negative. And that's true up until 2. At 2, the velocity goes to negative. And then we've got negative velocity and negative acceleration between 2 and 4. And then from 4 to 6, we've got negative velocity and positive acceleration. And then from 6 on, we've got positive velocity and positive acceleration. And we're going to use all of these characteristics to describe the motion of this particle. Okay, so from the beginning, the particle is moving to the right. How do I know that the particle is moving to the right? Because velocity is positive. It's moving to the right, but it is slowing down. I know it's moving to the right because velocity is positive, and I know that it's slowing down because the acceleration and velocity have opposite signs there. Okay, so let's continue. Then at time 2, it changes direction. The velocity goes from positive to negative. So it then starts moving to the left. At time 2. And starts speeding up. Again, it's moving to the right, or pardon me, to the left at t equals 2, because the velocity changes over to negative, and the acceleration is also negative since the velocity and acceleration signs are both negative there. That's indicative of the particle speeding up. So moving left because velocity is negative, speeding up because these signs are the same. Okay. From t equals 4 to t equals 6, the particle is moving to the left. Because velocity is negative, but it's slowing down because the velocity and acceleration have opposite signs. At time 6, it starts moving to the right. And speeding up. Moving to the right because velocity is positive. Speeding up because velocity and acceleration have the same sign. And there's my description of the motion of that particle based off of knowing its velocity and acceleration. It's a great description of the motion of the particle. All right, let's go ahead and we'll move on to example 5 here. For the given function f of x, f prime of x, and f double prime of x do not change signs. That means if I see that f prime is positive, it stays positive. If I see it's negative, it stays negative. Same thing for f double prime. So we're looking at this, and first of all, if we look at the change in our table here, when x is 0 to x is 1, f of x increases by 1. And then from time 1 to 2, or from x equals 1 to x equals 2, f of x increases by 2. And then from x equals 2 to x equals 3, excuse me, it increases by 3. The one thing you should see that whole time is the derivative has to be positive, because f of x is getting bigger and bigger, and since it doesn't change signs, f prime must be positive on the entire interval. Is f of x increasing or decreasing? It is increasing because f prime of x is greater than 0. Okay, and then is it concave up or concave down? So the question becomes, is the derivative, is the slope increasing as x goes by, or is it decreasing? Well, the slope from 0 to 1 averages out at 1 unit. The slope from 1 to 2 averages out at 2 units. Slope from 2 to 3 averages out at 3 units. And so the slope is getting bigger and bigger and bigger as x increases. So therefore it is concave up, because f double prime has to be positive, because these values are getting larger, and the amount that it's increasing by is getting larger and larger. All right. All right, that takes us to the end of our lesson on section 5.9. Go ahead and come back and join me next time, where we will be getting into section 5.10 of AP Calculus, which is an introduction to optimization problems. All right, see you then. Have a great rest of your day, everybody. Enjoy yourself.